Yeah, and I'm now going to share my screen with you. So it'll take me a second. Always ask me in a different way how to. Okay. Right, can we see our PowerPoint this morning? Miss, is that all up and ready?
All up, all good.
Brilliant. Can you also tell me if you can, in just a moment, because I will try and use this, if you can see these scribbles? Can you see those scribbles?
Yeah, we can see those scribbles.
Brilliant.
Yes is coming in.
Fantastic. Okay, so no, I've broken it now.
Yeah, good stuff. Thank you, guys.
So this morning you need to have a pencil, really, not just so you can jot down some answers and some of your thoughts as we go through. Nothing to share necessarily with us at all either. So, okay, so good morning, and today we're going to be looking at forces. Now, this is a new topic at secondary school for you, so you won't have covered any of this yet, but you will have done some things at primary school or junior school. And so our big question today is, what are forces and what is the difference between a contact and a non-contact force? So while we're settling in and getting ready, there are some keywords there: force, contact, non-contact, the idea of unbalanced forces and balanced forces, resultant and Newton. So these are some of our keywords for today. And then there's a little picture. And in that picture, you have got some people doing a tug of war. You've got Brian and Alyssa and Daniel and Maria. And I want you to just think about what that's showing and what might be going on and what might happen. So, Miss, if anybody puts any wonderful ideas into the question and answer box, please do tell me, just the first two, otherwise we'll get a lot of feedback, which we love, but we can't get to them all. So if anybody wants to write in the Q&A what they think is going to happen or what they think this is showing, go for it. I'll give you just a few seconds.
Right, so we've got Daniel and Maria are tugging at a force of 12 newtons, overpowering the other people.
That is absolutely fabulous. Brilliant. Who's that, Miss? We'll give them an achievement point.
That is Barney Munton.
Barney, that's brilliant.
And then we've got an anonymous that says, I think it's a contact force.
Good.
And then we've got one from Archie that says, Daniel and Maria are pulling more force into the tug, so they will win.
Fantastic. So looking at these images really gets us thinking about all this and helps us along. So what are we going to learn about today then? So we're going to recall the types of forces acting on an object and categorise forces as whether they're contact or non-contact. And then you're going to define resultant force. So that's the bare minimum we expect you to be able to do by the end of this session. And then we're going to have a little look at drawing force diagrams, calculating resultant forces and demonstrating forces acting on objects. And then those of you who are really, really pushing yourselves are going to predict the direction of movement using this idea of resultant forces. And you're starting just using that picture that we just looked at to have a little think about that already. So that's brilliant. So what do you know already? When you're at primary school, you would have talked about forces being pushes or pulls or twists. You know, if you pushed your little brother, that's a force. If you're pulling your bag off the shelf, that's a force. And so you have experiences of this language and these words, but we're now going to move on from using this language into using scientific language that is associated, that's linked with these words. So on this, there should be, oh no, this is cheating. On this sheet here, we've got some objects. We've got a floating duck. We've got a plasticine ball, which is attached to a force meter, also known as a Newton meter, which we'll use lots in the lab. You've got somebody carrying their shopping, person in bed, a bauble on the Christmas tree, and a floating boat. Now, every object has forces acting on it. There's forces acting on you right now. There's forces acting on your cup of tea, on your bowl of cereal. All of these things have forces on them. And Miss Stein wanted to know, how much do you know already about naming forces? Can you write onto your piece of paper that you should have with you before we go through it any of the objects, so if you pick the floating duck, just write letter A and think about the forces that are acting on the floating duck. Now I'm going to introduce a piece of information to you now, and that is that forces work in pairs, okay? And that's a really important piece of information that you need to remember. So I'm going to give you about 30 seconds just to have a look at these images. You don't have to do them all, pick one or two and see if you can name any of the forces that you've come across at primary school, because they don't change, forces are still forces, and see if you can tell us what you know already. So I'll give you 30 seconds to do that, and then we'll ask for a little bit of feedback. Miss, I also meant to ask, can you see my face? Because I get, when I share the screen, I'm not sure if you can or not.
Yeah, you can. It's not,
okay,
not in the same place where you can see it. It kind of comes up on one side.
It's fine. I can't see it at all. That's why I asked. So if I'm wildly gesticulating, whether you can see it or not.
No,
so
you come up on the side. So you're not in front of the slides at all. You're just on one side.
That's fantastic. Right, have we got any answers coming up in the Q&A box?
We've got a push, or they're coming in a funny order. We've got one that says, is the force from the picture A pushing on the duck, causing it to float?
So we've got some lovely ideas developing there. Brilliant. Any more?
We've got drag.
Oh, I love that.
Gravity, up thrust has been said.
Oh, these are fabulous. This is the language that we want you using. This is great. So what I'm going to do is I'm going to bring up the answers for you now, and we'll have a little discussion. So if we look at our little duck, we'll notice that there's an up thrust of water and there's weight. So the up thrust, when you're in the bath and you've got a rubber duck, I know you've all got your toys still, and you try and submerge it under the water, there's a force, and you can feel that force, and it's pushing it back up, and that's up thrust. And so you can have a look at all of the forces that are working in these pairs. We've got tension in the spring and the weight of the ball. When we have the weight of the ball, that's also dragged down by gravity as well. We've got the person carrying the shopping, they've got tension in their arm. You've got the reaction of the bed, so you've got the weight of the person and the reaction. If forces didn't act in pairs and the force was pulling you down to the ground, if you like, you wouldn't be standing up and you'd fall through the floor and all kinds of strange things would happen. So forces, we always, especially at this level, talk about them occurring in pairs. This is really important to start thinking and getting that into your mind. So there's some words there, this idea of up thrust, tension, reaction force, and weight. Okay, so these are some of the names that we're using, so we want to start you putting those into your head. With your task today, we've got some wonderful video clips for you to talk about forces, start to use this language a lot more. So you must look at the slides and look at the task that your teacher's given you for the questions as well, because that will help you. So what do forces do? Now, forces are amazing things. They're in action all the time. A force is something that when applied, it will change the motion or the shape of an object. Remember, motion is when something's moving. So if you apply a force to something that's moving, something will happen. So it could change the speed, change the direction, or change the shape. Okay, you know, if you squash a piece of plasticine, the shape has changed. If we were squashed, our shape would change. You know, if you apply a force to a ball on the table and push it, it will start moving. Okay, so there's all of these ideas that forces are involved in speed, direction, and shape. And these are really important ideas. So you must come and have a look back at the slides or the webinar or both. So this handsome chap here was Isaac Newton. And he did lots and lots of work on forces, and he came up with his laws of motion, which you will go into in a lot more detail, not today, but over the next few weeks, we'll start talking more and more about them. Now, Newton, because of all his work in forces, we measure forces in a unit called the Newton. And notice it's a capital N after Isaac Newton. Okay, he first theorised about forces, and then if you look below, there are two objects. There's a cartoony one here, where my arrow is there, and an actual real one. And these are what we call force meters or Newton meters. Okay, and so Newton meters measure forces. So here we've applied some mass to that particular Newton meter, and it will show you the force exerted. Okay. Just out of interest, does anybody know what the value given for gravity is on Earth? I'd be really interested if you pop it into the Q&A box. I wonder if anyone knows. It'd be an achievement point question. You can round it as well, so it doesn't need to be to the decimal, so you can round it. Miss, if anybody pops that into the box, let me know and we'll give them a shout out and an achievement point. So let's move on. I've popped up, I went onto the NASA website, there's another picture of Isaac Newton here, just to put on Newton's laws of motion. So one of the laws of motion is F equals ma, so that's force equals mass times acceleration. And the one that we're talking about a lot today is this idea of equal and opposite forces. So you have these forces in pairs. And then our other one here, which we will go into in more detail, is to do with how objects will stay at rest, or uniform means the same motion in a straight line unless there's a force acting upon it. Unfortunately, when we investigate forces, for example, you rolling a car along a desk, there's loads of forces that act upon it to slow it down and to stop it. In an ideal situation, we could remove all frictional forces, we could move air resistance, and so if that were the case, it would just continue going and going and going until something stopped it. So that's to do with Newton's laws of motion, but we will go into those in more detail. I'm just touching on those for now, for those of you who are interested. So looking at drawing force diagrams for objects. So we need to be able to show the forces, the pairs of forces in action on an object. So if we have a look here, there's a book on the table and it's telling us that the reaction force is 5 newtons and the weight of the book is 5 newtons. It's not moving, it's exactly stationary on the table. The size of the arrow should represent the size of the force. So the arrows here are the same size because they're the same amount of force, both 5 newtons. Now the direction of the arrow must show the direction the force is going in. So the weight of the book is pulling it down and the reaction force is going the opposite way. So they balance each other out. And as I said before, this other key piece of information, that forces act in these opposing pairs. Okay. Make sure that you always label your forces really carefully. And if the forces are balanced, the arrows will be of equal size. Now I've put here onto the PowerPoint, we call it, a little car, so we can talk about forces acting on the car. Now we know that the forces arrows have to point in the direction of the forces acting. So between our wheels and the road we have friction. I can spell this morning. And we have a thrust from our engine pulling our car forward. Okay, so those are opposite. Another opposite force we would have there would also be air resistance, but I'm just going to look at some of the opposing forces. Friction, and I'm going to put a circle around this, we're going to talk about briefly because it's a really useful force, but also it can be not so useful, and I'll mention why. And in fact, I won't. I'll see if you can in the Q&A box. But first of all, Miss, did anyone come up with the force, the amount of newtons for gravity?
Sorry, I was on mute. We've got a couple that have all said around the same things. They've said 9 or 9.8.
So the 9.8, the 9.8 one is perfect, and we would round it to 10 rather than down to 9. So we'd say around about 10, or 9.81 is absolutely fine. That's brilliant.
Someone else has said 10, a couple of 10s.
Fabulous. And while we're on the subject of friction, if you want to pop it into the box, why is friction useful? Don't make this really long-winded. Or why is it not so useful? So have a little think about that. Remember, frictional forces are where there's two surfaces that are rubbing against each other. It's very useful for me now if I had cold hands, because when we get friction and two surfaces past each other, we also get heat energy released as well. So there's another link to other aspects of physics there. Right, any questions, Miss Either, as well?
They're all coming in a funny order because of the times on people's computers. We've got one says when you're driving, so your car doesn't slip off the road. It can create
Brilliant.
heat. You can slow things
Fantastic.
down.
Oh, I have to interject there.
Nothing can stop without no friction.
We never create heat, and this is a real misconception here, and it is to do with language. We know what you mean is that heat is released, heat energy is released. We can't create the different types of energy. And if this is one thing that you take away in regards of energy, which is an aside to what we're doing today, is that you cannot create energy or destroy it. It's just transformed from one type to another. So we can't create heat energy, we release heat energy. Sorry, I thought I must simply get in there with that.
You've got another couple of quite nice ones that just say it cannot be useful because it can hurt you if you rub against something too fast.
Oh yes, absolutely.
So one that I think gets forgotten sometimes about friction.
Absolutely. If you slip over on the carpet or on the gravel, loads of you will have fallen over in the playground and grazed your knee, and that friction between the tarmac and your skin. Yes, absolutely. What a lovely, I actually haven't had a student say that before. So what a brilliant thinking outside of the box there. That's marvellous. We'll give an achievement point to that young person as well. Brilliant. So force diagrams, they show us the direction of the forces, the pairs of forces, and the size of the force, and we must label them. Okay, so let's move on. Let's get rid of that, and we will move on, if I can use a computer. So what is the difference between a contact and a non-contact force? Now, I'm going to say it again, I've said it before, we don't try and trick you in science. If something's in contact, it's touching. If it's not in contact, it's not touching. So contact forces act on objects that are touching each other. We talked about friction. Non-contact forces that act on objects that are not physically touching each other. If you think about two magnets, they're not physically touching, but they're either being attracted or repelled, and that's a non-contact force. So in this table here, it tells us some of the contact forces. We've got friction, we've got air resistance. And I know some of you might go, oh, but air resistance, how is that a contact force? Because what you need to think about is even though you can't see all of those air particles hitting whatever the object is, they're touching, and that's what's causing, a car to slow down. All those air particles are actually hitting, physically touching the bonnet, if you like, of the car. Then you've got tension forces and normal contact force. And then our non-contact forces are gravitational forces, electrostatic and magnetic. So gravitational, we can't see, they're what keep us on the earth and stop us floating away and living a very different life. And magnetic, I just mentioned. And then electrostatic are the forces, I suppose when we're talking about atoms and things like that, that keep the subatomic particles in an atom where they are and things like that. And then you'll do things to do with all sorts of other things to do with electrostatics. Brilliant. So we've got our contact forces and our non-contact forces. Again, more key information. And we know that we're trying to get a lot of information into you today, and it's a new topic. But this is like our start-off lesson. So we'll then be taking these ideas down different avenues over the next few weeks as well. And Miss and I have got some amazing practicals planned for you to do at home next week. I say planned, we're planning them, aren't we, Miss? So here are some more images again, just to reflect some of those words that we just used. So if we look here, I'll put my pointer on so we can see. We've got our force here. Is that a contact or a non-contact force? I'm sure you all said non-contact because it's magnetism. Okay, we've got our air resistance here. We know that that's a contact force because the body is falling through the air and it's hitting all of those air particles. Whereas gravity, our non-contact force, is pulling it down to earth. Again, we've got the apple falling from the tree. We've got gravity. We've got this person roller skating. So you've got a pair of forces there. Don't forget that. You've got some air resistance and you've got gravity, pulling the person down the hill. You've got your matches. You've got frictional forces. If you didn't have frictional forces, those matches wouldn't light. Okay. And so there are some ideas for you about the contact and non-contact force. And if we think back to our picture at the beginning of the lesson of the tug of war, we've got that tension force there as a contact force too. And then we've got our weight and normal force. So we're starting to hear all this language to do with forces. And so we'll just go through one here. Have a little think about here. Just checking, what do you think the forces are here? What are the forces in action on our apple falling out of a tree? There's a couple of things you could put. Miss, if anybody puts the pairs, it doesn't matter which order, we don't mind, the pairs of forces into the Q&A, we could see what they were coming up with.
Yeah, we'll do. There's a couple coming in now. So we've got gravity and air resistance.
Lovely.
Gravity, push and pull. Let's try and scroll through. Mostly we've got gravity or gravity and air resistance.
Fantastic. And I think one of the lovely things there, and this is why we're doing an understanding check, is we now want to move away from the language of push and pull. We want to start which force is doing the pushing and which force is doing the pulling, if you like. So here we've got gravity pulling it down to earth, and some of you talking about opposing it, pushing it away, is air resistance. And so rather than using the terms push and pull, what forces are those pushes and pulls? And that's why we do this. We get a little an idea of what's going on. Miss, I think we'll do a poll now. So I'm going to try and see how this, if I can still do the poll. Polls, brilliant. Forces. And let us launch it. Have a little go, guys. What have we got? Let me give you some time to read. Oh, I put a tricky one in that first question. Think, who was the man who did lots of experiments on forces and came up with the forces of the laws of motion? There's a hint for you. Oh, there we go. And I think one of the things then is always, always, always carefully read the question. Those of you who launched in with less than like a second didn't get the correct answer. So what unit of forces what unit do we measure forces in? True or false about the pairs? Oh, lovely. I haven't even told you this yet. We started talking about it. Which force wears down our brake pads and tyres or stops us from slipping over? Which force causes apple to fall to the ground? Which of these are non-contact forces? Do you know, I don't think I allowed you to choose more than one. I think that was my fault on there. So if you picked one of the correct answers, that's great. So I think we'll just give you another 20 seconds. But most of you voted now. 20 seconds. Are there any questions coming up there, Miss?
Not really. No, they're all getting on with their poll. There's a couple that I'm typing to answer. But nothing to talk through.
Fantastic. So another 15 seconds. So you've had 2 minutes, and then we will feed back. Another 9 seconds. Brilliant. So let us end this poll. So those of you who answered newtons for the unit of force are correct. That was 79% of you. I was a bit cheeky and I put neutrons in as well, just to see how your spelling was. So, and I also put it with the capital as well. So yes, that was me tricking you. So it's newtons, not neutrons. Neutrons are a particle inside the center, the nucleus of an atom that have no charge. Forces come in pairs. 86% of you correct there. Brilliant. And this one I only allowed you, unfortunately, to choose. Oh no, I didn't. This one is friction. Which force wears down our brake pads? So if your bike, you've got the brake pad against the metal of the wheel, the tire, and every time you squeeze that brake pad to slow down the bike or to stop the bike, it touches the metal of the wheel, and that stops it or slows it down. And so you can imagine that wearing away over time through friction. So well done with that one, all 66% of you. Then 85% of you, gravity, apple falling to the ground. Which of these are non-contact forces? If you chose magnetic, fantastic. If you chose electrostatic, which I've spelled incorrectly, I do apologise, I've missed a T. And if you chose gravitational, you'd be correct. Friction and tension are contact forces. Remember, contact is where they're touching, and that tension, pulling, the tautness of a rope or a wire or whatnot, is a contact force. So for the most part, actually, you did very well. So this is really good. That's good for Miss and I to know. Let's just close and we reshare. And now we're on to resultant forces. So at the beginning of the lesson, you had to look at that picture of the people doing the tug of war. And on one side, we had 10 newtons, and on the other side, we had 12 newtons. And all of those of you who answered said that the people who were pulling with 12 newtons would win. They would win the tug of war. And essentially, you are correct. And we're going to see a little bit now about what that means in relation to resultant forces. So when two objects push or pull on each other, they exert equal and opposite forces on one another. For example, as I said earlier, if you're pushing down on the floor is pushing back up on you. Otherwise, you would fall through the floor. If you have lots of forces, in this word multiple, many, acting on an object, you can replace them with one single force that has the effect of all the other forces combined together. And that single force is called the resultant force. Okay, so here we've got our driving force, our thrust from the engine, and our air resistance. If our driving force was 15 newtons and our air resistance was 10, can anyone tell me what would happen to the car? Would it keep going forward? What do they think the overall force of the driving force would be? Wonder if anybody's got any ideas. And let me know what you come up with. And don't worry at this point if you don't understand. We're just checking and getting you thinking. Which force is going to have the greatest effect? You already know it's that driving force. And thinking about here, you can replace them with one single force that has the effect of all the other forces combined together. What do you think the value of that force might be? Miss, have we got anybody putting anything into the Q&A?
Yeah, we have. We've got some saying that it would go forward. We've got some saying that we've got 5 newtons.
Oh, the 5 newtons? What does that? Oh, I wonder what that means. I wonder where they're getting that from.
Really nice one here. It says it also depends on the level of friction.
Oh, these are lovely. Absolutely brilliant.
Driving force will overpower it by 5 newtons.
Fantastic.
Driving force is the greater force. Some great use of the language and use of numbers here. It's really, really good.
And I mean, this is fantastic. And some of you will now who didn't put that be going, oh, where did they get that 5 newtons from?
Yeah.
Oh, okay.
People saying I'm confused or I don't understand.
Oh, that's all right. Remember, this was just a thinking moment. We haven't told you what resultant forces are or gone through. Well, we've mentioned them, but we haven't explained to you how we calculate them. I just wanted to see if you could give them some information, if you could have a go at that. If you can't, that's absolutely fine. That's what we're learning. Okay. So let's have a little look then at what we mean by this. Right. So we've got a rocket here and it produces a thrust of 2,000 newtons and it has a weight of 1,000 newtons. What do we think the overall force on the rocket is? So that resultant force then that we're talking about is the overall force that's in action. Now, if we have here, use my pointer for you. If we have here, this thrust is 2,000 newtons and it's got a weight of 1,000 newtons. We can all happily say that it's going to be going in that direction. Now, the question is, what is the force of it going in that direction? Well, the beauty is that we can work it out. So if over here, our weight is 1,000 newtons, if I could write 1,000 newtons, and up here is 2,000 newtons. If the weight is pulling it down by 1,000 newtons and the thrust is 2,000 newtons, we can say that the overall force is 2,000 minus 1,000 newtons, and that will equal 1,000 newtons. So have a little look, and I'm going to give you a moment to think about how I've worked out that the thrust, therefore, dear, thrust is still driving it up towards space, if you like, and the resultant force is 1,000 newtons. So have a little look and think about how I've come up with that. Any questions in the Q&A, miss?
We've got a bit of silliness going on.
Oh, no silliness, young people, no silliness.
So, unfortunately, spoiling it for everyone because I'm having to deal with that rather than answering people's questions. But we've got a question here, which I was just going to type to answer, actually, but it might be quite interesting to talk about it. It just said, if you were going to build something, would you have to factor in the thrust and the weight? So I'm assuming that's if you were building a rocket. I'm assuming that's what this question is around. So you would have to factor in the weight of the rocket and the amount of thrust that it could produce in order to have an idea of how fast it could go. So I was typing that one out.
That's a really lovely question, and actually, if you think about this on a large scale, those who are in, you know, aerospace engineering, that's what I was going for, and they have lots of things to consider. You're absolutely right. The fact that you've thought about that is fabulous. So not only do they need to consider the thrust of the engine, they also need to consider the amount of load on board, because that will impact how much thrust the engines will need to overcome the force of gravity as well. So there's lots of things that they need to consider, and there's loads and loads of these maths to get your rockets into space. And unfortunately, if they do that wrong, well, you get some disastrous outcomes. I mean, they even take into consideration the mass of the astronauts and things as well. So all of those things have to be taken into consideration. On a smaller scale, if you were making a little rocket at home, you'd absolutely consider the thrust from your, I suppose, your whatever propellant you were using, whether it was a water rocket or a vinegar and bicarb small rocket as well. You can do that as well. It's a bit smelly and they don't go very far, but it's still quite fun. So yes, absolutely. And what a lovely question, and what a lovely way of thinking. Miss, anything about the answer to our resultant force here?
Answer to resultant force, let's have a little look. So someone's saying it'll be going straight up because the thrust is 1,000 newtons more than the weight.
That is perfect. That is a brilliant, brilliant answer. And you just say that the resultant force was 1,000 newtons. That's marvellous.
Yeah, so we said there's more thrust when you subtract it. There's no more weight and 1,000 thrust. There is still weight there. It's just balanced. Yeah, the weight is still there. Just the thrust is overpowering almost.
It's greater than. Yeah, absolutely. It's greater than. Okay, these are great
ideas.
These are lovely ideas, in fact. Right, let's move on.
I'm taking names for achievement points as well.
I think we'll move on from this one as well, because I feel like we're taking a lot of time. We'll very briefly, no, we'll leave you guys to have a look at these. We've put some into a PowerPoint for you to have a look at, and all the information is there, and you can look back here. I was going to do balance forces, Miss, but I think we might have to leave that until next time. But what we will do, Miss and I talked about this, is we'll just very quickly look at this here. You've got a trolley. It's very simple. You've got some applied forces here. This helps us to understand, again, the resultant force. We've got 20 newtons in this direction and 40 newtons in that direction. The resultant force is 20 newtons because you take away that from that, and we know that the motion is in that direction. Here, 25 minus 25 means that the resultant force is 0. And when the resultant force is not 0, it means that they're unbalanced, and there will be a change in the behaviour of that vehicle. If it is in motion, so if it is moving, there'll be a change. If it was stationary, it would stop moving. Really interestingly, we do have 0 resultant forces when vehicles are moving. it means that the forces are balanced and that they are going at a constant velocity. There's no change because the resultant force is 0 and those forces are balanced. I will just leave that there with you. And I think, Miss, we will leave it there today, as otherwise we will run on too long and I want them to get a little break before their next session. So are there any questions? And while you're thinking of your questions, don't worry about this slide that I've just put up here. That's to get you thinking for next lesson, for next week. You don't need to know all the answers. It's to get you thinking.
There's just a couple of questions on what's the work, and some saying that I've had a little look in the Google quiz, and it's just a recap. So when you go on to the Google quiz, the first section is recapping last week. So we're doing a little bit of revision, really, really important. But if you scroll down after, I think, question 6, it goes on to some forces questions. And then after that, there is another set of PowerPoint slides, which your teacher will put in your Google Classroom, and there's some videos and some little questions to have a little look at. So go into your Google Classroom, your teacher will have told you what all of your tasks are in there.
Yeah, thank you again. Some just brilliant answers and totally amazing engagement. We couldn't be more proud of you. Keep it up and keep challenging yourselves. Challenge us, ask us questions. I mean, the questions about forces are really interesting, like the one about the rocket and building things. So it's lots to discuss as well. So well done, Year 7. We are incredibly proud of you, and you can now go and do your work. Any questions, ask your teacher or post in your Google Classroom. For my classes, I'll go into the Google Classroom now for any questions. Okay, take care, everyone. Thank you, Miss.
Thank you.